Good morning. Thanks for attending this, our fourth webinar focused on time series forecasting and anomaly detection. If you want to catch up on our previous webinars in this series, visit our YouTube channel. My name is Philip, I'm responsible for strategy and business development at Bardis, and I'm joined by Daniel, our lead data scientist. Today we'll be talking about doing anomaly detection to help drive efficiency in your production plants. Just in time, lean, Six Sigma, TQM, Kaizen, responsive supply chains, and the 5 S's. What do all these fads have in common? They were and are efforts to drive efficiency in every process, from the supply of raw materials through manufacturing, warehousing, to outbound logistics and everything in between. Manufacturing leaders have looked everywhere to squeeze more out of less. Bottlenecks in one process can actually result in disruption along the whole entire system. So detecting problems as soon as they happen or before they happen is vital. Industry 4.0 is a collective term we can use to describe all these process improvement strategies. It's another way of saying 4.0 is what digital transformation might look like for a manufacturing company. It's the fourth industrial revolution. It's revolution in manufacturing by providing companies with the opportunity to utilize advanced capabilities and digital technology throughout the product lifecycle. As a result, manufacturers are benefiting from increased visibility into operations, substantial cost savings, faster production times, and the ability to provide excellent customer support. So let's look at 3 trends that are ushering in Industry 4.0. IoT is the next big thing. Roughly 63% of manufacturers believe that applying IoT to products will increase profitability over the next 5 years. They understand that IoT empowers them to make informed strategic decisions by providing crucial real-time information. Predictive maintenance is all about keeping production on track. A breakdown in critical equipment is costly, both in terms of repairs as well as downtime and loss of productivity. The widespread adoption of predictive maintenance technologies could reduce companies' maintenance costs by 20%, reduce unplanned outages by 50%, and extend machinery life by years, according to McKinsey & Company. And then leveraging the supply chain for competitive advantage means that to remain competitive, we need to deliver more value to our customers than our competitors. Savvy manufacturers will continue to distance themselves from their competitors by leveraging new technologies. This will enable your company to operate your business more efficiently, with more visibility and control over inventory, reduction of operation costs, and improved customer satisfaction and retention. And today's supply chain technology solution cover a variety of manufacturing needs, including manufacturing optimization, logistics optimization, sales and operations planning, product lifecycle management, network and inventory optimization, RFID, and procurement. So let's have a look at one example and get down to basics. Let's look how we might use machine learning to improve OEE, overall equipment effectiveness. It's really a measure of how close you are to perfect production, or another way of saying we only manufacture good parts as fast as possible with no stop time. There are 3 components or 3 factors in OEE: Q for quality, P for performance, and A for machine availability. If we multiply these, we get OEE. Let's have a look at an example. You can see here on week 1, 85.1% OEE, and we are happy because on week 2, we improved OEE to 85.7. But let's understand how these 3 factors might give us more insight into what's going on underneath the covers. As you can see, very few production managers would be satisfied with improving OEE at the cost of quality. And by knowing where to look is the key to controlling and managing your OEE. So how do we How do we increase our OEE? We need to reduce the 6 big losses that have been identified. And using anomaly detection, we can help remediate the impact to OEE proactively. So if we look at these 6 losses, there's 3 candidates: production rejects, reduced yield, and equipment failure, that are ideal candidates for anomaly detection. It can be argued that anomaly detection and forecast can be used in identifying problems in all 6 areas, but these 3 are the ones we see most obvious and easy to implement. Predictive maintenance relies on being able to find anomalous data coming in from your sensors. We need a resilient option, one that can handle real-world data volumes, velocities, and availabilities. A broken sensor, for example, should not render your entire machine learning model useless. To instantly rebuild your machine learning model on the fly is what we hope to present you today, and it represents a breakthrough in how forecasting and anomaly detection can be implemented in your IoT or predictive maintenance solution. Simply put, the opportunity to improve business on a significant scale are too valuable to be left unexplored. And IoT data has left this opportunity wide open for most organizations working with machinery or anything that captures sensor data. The obvious, yet enormously impactful case of predictive maintenance is just the beginning of the potential we will see from the steady reduction in the cost of capturing data and calculating predictive outputs. We at Bardus see the inexpensive cost of IoT and machine learning coming together to reshape operations for our customers today across almost every industry. So how do we find anomalies? We essentially need to build a forecast and then compare that forecast to the actuals. So we have a timeline with a past and a future. We sit at the present point in time, and we want to know what is the value of our target variable at some point in the future. Predicting those future values depends a lot on the actual historical values that we've collected from our sensors. It also depends on many other factors that influence that target variable. These factors are called features by data scientists, and taking those features into account, as well as the fluctuations of our target variable, allow us to create a multivariate forecast. Once we have a good multivariate forecast, we can compare the actual readings streaming in from our sensors, and if they fall outside a predetermined threshold, we can flag that as an anomaly. So a few words about TangentWorks, which is the core engine driving this anomaly detection today. It was named one of the top 10 most innovative machine learning companies in 2019. It's fast, automatic, scalable, and easy to deploy forecasting and anomaly detection solution. It works by finding the right features, not the right algorithm. And deploying it is simple. You can do it on the cloud, on-prem, as a web service, or on the edge. It's already integrated with a host of data products and data technologies, including Siemens IoT Gateway from Azure and from AWS. And it's priced on a consumption of forecast model, not how it's consumed. At the end of this, you'll also see there's a link for a free trial, and we'll send that in an email as well, so you can get started right away. Bardus is a data company, and what we also started to do is take it from not only from the IoT use case, but also have started to implement data anomaly detection in some of our data solutions for our customers. At the data warehouse level, we can track data coming in through certain from the tables and databases that we are capturing data on the ingest side. And by using TangentWorks, we're able to do anomaly detection on the data coming in there. And then we can also do it on the consumption level, where the users are actually looking at how KPIs may have changed and using that anomaly detection there to basically provide a level of alerting before things get out of control. So what are we going to show you in the demo? The use case is anomaly detection in a multi-stage continuous flow manufacturing process. Daniel's going to dive you into Tim Studio, which is the TangentWorks web platform. It's going to create a model on the fly. He's going to dynamically add and transform features. He's going to compare those features, those predictions with the actuals, and then use that to detect anomalies. And he's also going to show you what's called explainable AI, which allows you to look under the covers and understand what features are driving that forecast and that anomaly detection so that you understand where these problems can be solved. It's also going to show you TIM in Excel to show you how easy it is to do a forecast in Excel, and also show you in a more sophisticated integration with ClickSense. So Daniel, over to you. Show them the demo, and we look forward to catching you on the other side with questions and answers, and also access to our contact details and the free trial. Thank you, Daniel. Take it away.
Okay, thanks, Philip. So for this demo, we're going to be looking at a dataset from Kaggle. The data is from an actual production line near Detroit, Michigan. The authors don't say exactly what this dataset represents, or exactly what is being produced by this production line, but it is from a real production line. And it is a high-speed, continuous manufacturing process with both parallel and series stages. So if we look at that in more detail, in the first stage, there are 3 machines, 1, 2, and 3, that operate in parallel and feed their outputs into a step that combines the flows. Then the combiner machine produces some product output, and there are 15 measurements which are made on that output. So the idea is that these 15 measurements are the main measurements we're trying to predict here and look for anomalies. So there's also a second stage where the output from the first combiner machine flows into a second stage with 2 machines, 4 and 5, and these process in series. So machine 4 takes the output from stage 1, and machine 5 takes the output from machine 4, and then some more measurements are made to the product in the same 15 locations. So these are also some measurements that we could be running anomaly detection on. So for the purposes of the demo, we're just going to focus on detecting anomalies in one of these fields, and I can show the fields in a bit more detail down here. So firstly, notice that we have a timestamp column. So this is vital if we're going to be doing time series forecasting or time series anomaly detection, which is what Tim specializes in. So a time series is something that has a timestamp column with regular intervals. So you can see this is moving up in seconds. So in terms of the data we're trying to predict, let me just scroll across. You can see there are a lot of fields in here. So we're going to be looking at the stage 1 output measurements. So you can't see the whole title, but there are 15 of these measurement fields: measurement 1, measurement 2, measurement 3, and so on. So we're just going to select a single one of those. We're actually going to use measurement 2. And then there are various other fields which will be used as input to the machine learning model which Tim will build. So these other fields will help us to understand whether or not a certain data point is really anomalous or not. And will also give us an idea of what is causing that anomaly. So we have some information about the ambient environment. Again, you can't see the title, but this is temperature and humidity. So we have information on ambient conditions in the room where the machines are being operated. And then we have various information about each of the machines. So we have information about the raw material going in, and these process parameters represent the temperature measured on the machine in a couple of locations, the amperage on the motor, the RPM on the motor, and then there's some material measurements as well. So I think this one measures the pressure on the material being operated on by the machine. This measures the temperature on it, and so on. And we have that same information for each of the machines. So we have the same stuff for machine 2, machine 3. Since we're only looking at the output from the combiner at the end of stage 1, we're only looking at machines 1 to 3. But of course, machines 4 and 5 also have these same measurements as well. So for a full production pipeline, you would want to consider running anomaly detection for all of those fields. Okay, so now let's take a look at Tim's studio. So this is the web platform that TangentWorks provide for working with TIM. TIM is the algorithm, TIM Studio is the web platform. So there are a number of different ways to work with the TIM algorithm. You can also work with it through a web API. There are also extensions for Excel and for a range of BI tools like ClickSense, and there's Alteryx and Power BI and so on. And I'm going to be showing the integrations with Excel and ClickSense today. But for now, let's stick with the web platform TIM Studio. So firstly, we can see the data that I've loaded in here. So this is showing a time series of the stage 1 output measurement that we're going to be predicting anomalies for. So we can see this output here. We can zoom in and zoom out. We can layer in some of the other variables which we hope TIM is going to use to help detect anomalies. So these are the temperature and humidity. Then we have some other parameters as well. So to start building a model with this, we switch to the model building definition page. So the first step is to add a new model building definition. Let's call this stage 1 output anomaly detection. I'll call that 10. That will become clear in a moment why I call this 10. And we're going to call this residual fluctuation. And I'll also be explaining why I call that later on. Okay, so what we're doing right now is we're just setting up the parameters for this model that we're building. First we have to choose the dataset, so we already know that's the dataset we want to work with. So one of the main parameters we have to decide upon is the sensitivity. So this basically says like how much kind of signal to noise are we getting? Like with high sensitivity, we'll be getting a lot more anomalies detected, but there may be some noise coming along with that. There may be some data points which are detected as anomalies but are actually not really anomalous. So you can try out different numbers for the sensitivity parameter. I'm going to go with 10 for now. So normally you might sweep through a few different options for this. But having said that, the TangentWorks team are actually going to be implementing an automatic sensitivity decision algorithm, which will decide upon the most appropriate sensitivity for this data set. Of course, you can still set that manually, but being able to do this automatically will be a big help. So the next set of parameters we want to look at, we need to change a few of these parameters here. And notice that we have some parameters for what's called a normal behavior learner and some for what is called an anomalous behavior learner. And we'll be returning to that later, and I'll be explaining more about what this actually means. So I'm going to remove weekday transformations. And we want to be detecting two different types of anomaly, basically. Or two different approaches for detecting anomalies based on residuals and fluctuations. And again, I'll explain this in more detail later. But for now, this is really just to show kind of how to go through the steps of building a model. So everything so far has been building the model definition, which defines the parameters for the model that we plan to build. Once we've done that, we click on Build Model, and that will actually build the model using those parameters. So the model gets added to the queue, and so now the model will start to be built. And this is where we can compare TIM with other approaches. So there are other automated machine learning approaches around, but most of them use a brute force approach, where basically in forecasting and in anomaly detection, you have a range of input variables going in. So we have the ambient temperature and humidity, various other measurements for the machines. But we have to transform those to make them useful for a time series anomaly detection problem. So we might take moving averages, we might take lags of those parameters, and we don't know ahead of time which the most appropriate transforms are. So the way some other automated machine learning tools work is that they take a brute force approach to this, which is okay. That can lead to decent results, but it's also quite slow and takes a lot of compute. it can take like half an hour to an hour even for a small data set. So with TangentWorks and Tim, I don't know if you saw while I was talking, but the model finished building within sort of 2 or 3 seconds. And that is because Tim has a much more efficient way of finding the feature transforms. So that's what makes this such a revolutionary tool. Being able to build these models, both forecast models and anomaly detection models, so quickly really opens a lot of doors for what you can do with the tool. So now let's look in some more details at the model that we just built. Okay, so what we see here, again we see the blue line representing the actuals, the output from stage 1. And the red blobs here are the anomalies which Tim has detected. So you can see that Tim is not simply just sort of detecting the highest peaks, like for example this one has not been detected as an anomaly. So it's not just looking for high and low values, it's actually much more complex than that. It is building a full forecast model. The purpose of the forecast model is to determine normal behavior, i.e., so we could consider this sort of range as perhaps normal behavior, maybe this range as well, and then we're looking for deviations from that. So we compare the forecast prediction to what we actually see in actuality. And so that's kind of what we see in this chart here. This is kind of showing the difference between the forecast and the actual data. Now it's a little bit more complicated than that because there are some tricks which TangentWorks uses to detect different types of anomalies, which I'll go through in a second. But first, also note this pink line. This represents the sensitivity threshold. So remember, we picked 1 for that before, or rather 10, I think. But this line sort of indicates the sensitivity such that any points above this line will be detected as anomalies. So you can see these red blobs here, all of the points which are above this line here. So you can imagine if you use a different sensitivity, if this line was a little bit lower, then you might be detecting more anomalies, but some of those might actually be okay. Like maybe you'd be detecting these, which maybe these are anomalies, maybe these are actually just kind of expected deviations. So you can adjust that sensitivity parameter based on the amount of signal to noise you really want. But like I said, it will soon be possible to determine this threshold automatically. That's a feature that should be coming in the next few weeks from TangentWorks. So the other thing we can see here, as well as the actual anomalies that have been detected, Tim also gives us an idea of which of the input variables are contributing the most to detecting anomalies. So this is very important sort of within the field of explainable AI, which is a sort of a big trend at the moment in the data science industry, both in research and also in industry from the point of view of business use cases. Like if we think about forecasting more generally, then it's very useful to be able to get predictions out of an automated forecasting tool, but it's also often helpful to understand the drivers behind those predictions. So in this case, was the output anomalous because of the ambient conditions, ambient temperature, humidity, or some issue with one of the machines, one of the 3 machines that operate before stage 1. So we can see the features which are contributing to the predictions here. So we see, in this case, the most important feature, because these are ranked based on their importance for the predictions. The most important input variable or feature is one of the temperature measurements on the combiner machine. Okay, so probably makes sense if maybe the combiner machine is running hot or something, then that could be leading to defects in the product. And then we also see in this case the other temperature measurement on the combiner, temperature 1, and also the ambient temperature in the room. Now this particular feature is what's known as as a interaction term, because it's taking information from 2 features. So this indicates there's probably some kind of correlation going on between the ambient temperature and the temperature, this temperature measurement on the combiner. So perhaps this indicates that the ambient temperature in the room is the cause of the machine going wrong. It's just a theory, but this sort of analysis can help you understand that sort of thing. and so on. And also, just to note, these transforms, some of this data is transformed. So, for example, we have a sine transform here. So that obviously will take care of periodicity in the data. So if there are certain kind of repetitive periodic patterns in the data, that can be modeled using this type of transformation. So this kind of shows, like, in more detail about the some of the complexity which TangentWorks is using to build these machine learning models. And this, understanding and deciding on what these feature transforms should be. So deciding should you use a sine transform, or should you take a lag or a moving average? What should the window be for the moving average? What should the periodicity of the sine transform be? These are all things you don't really know ahead of time. So TangentWorks has this algorithm which can find the optimal set of feature transforms which give the best performance for a particular forecast model or anomaly detection model, whereas other tools use a brute force approach, which is much slower. And since TangentWorks is so fast, like I said, that opens up a lot of doors. You can imagine doing anomaly detection at scale. Let's say you have thousands or tens or hundreds of thousands of fields in your data warehouse. You can imagine scaling this up and applying anomaly detection to all of those fields. Another thing you could imagine is integrating this into a BI tool. If you have a BI tool and you want to select some data and run it through anomaly detection or run a forecast on it, well, you don't want to be waiting around half an hour to get results back like you would with a brute force machine learning tool. Since TangentWorks is so fast, you can really work with the BI tool very effectively like that. You can do one forecast, maybe change around the parameters a little bit once you get the results back, and kind of work iteratively to build a good forecast or anomaly detection model. Okay. So next I'm going to compare to another model which we built, because if you remember from the model building definition, we were looking for we looked at two different approaches for detecting anomalies based on residuals and fluctuations. So actually first we're going to look at the TIM Studio documentation so we can understand that a little better. So this page goes through some of the basics of different types of anomalies. Anomaly detection is a difficult field because there are many different types of anomalies. Even defining whether something is actually an anomaly or not can be a difficult question. And so there's a nice article on the TangentWorks documentation. These links are all public, so if you're interested, you can take a look for yourself. So let's go through some of the types of anomalies. So first we have point or global outliers or anomalies. So these are kind of the simplest type of anomaly to detect. It's a data point that is basically far outside the normal behavior for a given data set. And this is kind of the most simple type and also the most obvious type. And perhaps for that reason, that's why a lot of research has been focused on these types of anomalies, but a bit less research on other types of anomalous behavior. So another type of anomaly is a collective anomaly. So this is where we see a series of points that the way that they occur together is quite different from other patterns seen in the data. So you can see that these points are looking very different from the behavior that we usually see sort of within this peak. Looks like on other days within this data set. Another type of anomaly is the contextual anomaly. So this is where like a single point appears to be anomalous, again, compared to the context. So compared to other similar kind of patterns that we see maybe on another day. So we can see this point looks quite different from the pattern that we usually see on each day here. So these are some of the different types of anomaly we need to detect. One of the important things to point out is that, I said it's complicated to decide exactly what is an anomaly and what is not. Kind of the starting point for deciding is to decide what is normal behavior. And if we're approaching this from an automated machine learning perspective, we therefore have to, once we've decided what is normal behavior, we need to build a model which can predict and detect normal behavior, and then also detect deviations from that normal behavior to detect anomalies. So now let's look at another documentation page on the TIM website. So this goes into a bit more detail about how TIM tackles this problem of detecting anomalies. So let's say we're getting some data from sensors. This is unlabeled data, meaning that we don't know what the anomalies are already. If you know what the anomalies are, or if you have historical cases of anomalies, you can actually approach this differently as a supervised learning problem. But in most cases, we don't exactly know when the anomalies occurred historically, so we're just taking these patterns of data and trying to find anomalies in them. So the first step that Tim takes is to build a normal behavior model. So this is something that is basically a forecast model and is trying to basically be able to predict the normal behavior for that sensor, for the data from that sensor. Now, once we have that, the simple way to use that is to compare the predictions to the actuals. Let's say we have more data streaming in, and we've pre-built our model, and we want to compare the predictions to actuals. So that's kind of the simplest way of doing it. You could just look at cases where the difference between the prediction and the actual, which is known as the residual, is beyond a certain threshold. And that is one thing you can do with TangentWorks, but there are other ways of looking for anomalies. So like I said, we can take the residual approach. So on this sort of example dataset that TangentWorks provides, these are the anomalies that would be detected on this dataset. However, you can also look at the residual change feature instead of just residual. So this is looking for changes in the residual. So it's basically looking for when there's a sudden change in the residual. We go from having a low residual to a high residual here. So this is helpful if you see like a sort of sudden deviation, where it's really the sudden deviation which is the anomaly, which you're trying to detect in that case. Another type, fluctuation anomalies. These are cases where basically the fluctuations, i.e. the usual kind of range of data that we're seeing, you can see it's much decreased here and much increased here. So in this case, these points would all be detected as anomalies. Again, you can look at fluctuation change, where you're just looking for a change in the fluctuation amount rather than detecting all of the anomalies. This can often be effective for certain types of anomaly detection use case. And the final type of anomaly detection is imbalance. So this is where we're seeing the fluctuations are staying the same, right? So the kind of average deviation from the mean is roughly the same within here, but also within this section and also within here. The difference is that the overall mean, the average behavior, is shifted in this case and also over here. So these are the anomalies we detect. And again, there's an imbalance change version, which just detects the initial change. Okay, so if we go back to Tim's studio and look at the predictions we had, so the model that I had built before was using both residual and fluctuation. So it was looking for anomalies in both the residual and the fluctuations. But we can compare that with other models which have been built. So let's first look at a model which was built using only or looking only for fluctuation type anomalies. So this one is a little bit different. It's not picking up as many anomalies because we're not sort of basing it on the residual. Notice some of these points not being picked up as anomalous, and others are. So again, it's not a simple sort of just looking for outliers in the data. It's a much more sophisticated anomaly detection model. Let's look at another example of a model which in this case is built looking for imbalance type anomalies. So the approach for this one is a little bit different, which is why I'm on the detection page here instead of the model building definition. And I've pre-built this model. So what's happening here is that I trained the model on this set of data, so that the model learns that this is it tries to detect normal behavior from this. Now notice that my training data actually includes what might be some anomalies here, but it's basically picked up this sort of region as probably the most it's the most normal behavior. So you can see that when we apply the model going forward to data the model has not seen before, it detects this region as anomalous and also this region, because you can see this is also kind of shifted from the average that we had here. So, because if you look at this data set, there is quite a substantial change in this measurement, going from this initial area, kind of shifting up a lot here and then down, but still not being close to the original normal behavior. So through adjusting these parameters, you have a lot of flexibility, a lot of different approaches for detecting different types of anomalies. And this is one of the important aspects of anomaly detection. Ideally you would need to have some domain knowledge to understand what should be considered as an anomaly. But once you know what should be an anomaly and what is normal behavior, TIM gives you the flexibility to enable you to create these powerful machine learning models for detecting these anomalies, and for doing that very quickly. So one other point to mention is that you can, if for production use case with this data set, ideally you'd want to be running anomaly detection for all of the different measurements for the product, probably both from stage 1 and stage 2. So if you wanted to do that, you could just go through the tool and do this, but probably more likely you'd want to automate that using the API. So everything that I showed you in the TIM Studio platform can also be achieved with the TIM API. In fact, really the way it is that the TIM API is kind of the first thing that was built by TangentWorks, and then the TIM Studio platform was built on top of it. So it's kind of API enabled from the very beginning. So it's very sort of programmer friendly, very much a tool that you can work with from a programming interface effectively. Okay, so I also said that I would show the Excel and QuickSense integrations. So let's switch to Excel first. I'll make this a little bit bigger. So we see the same data set here. We have our timestamp. Stage 1 output is what we're trying to predict, and then these other input variables. So to make so in this case, I'm actually going to make a forecast because in the Excel and also in the QuickSense integrations, the anomaly detection feature is not yet supported. However, that is under active development and will likely be available quite soon, within the coming weeks. But for now, I'll just show an example of how to build a forecast model, and you'll see how kind of quick and easy it is to do that with the Excel plugin. So I just open up the TIM extension. We decide on the range of data we want to work with, select the target. We want to predict stage 1 output, and then select all of the predictors. Then we just have to select how many time steps we want to predict ahead in the future. So I'm going to select 96. I hit the forecast button. That is going to package up the data and send it over to the TIM algorithm API, which will then build a model. As we're waiting, it's building an entirely fresh model here, doing all the feature transformations and so on. It's generating all of those different transformed features and the interaction terms that we looked at before. And then once it's done, it just adds the forecast to the end of the spreadsheet. So it's very cool how fast it is. Excel is not the most exciting tool for showing results from this. You can see a bit more detail on the TIM Studio platform, but it's great to see kind of how easy to work with this thing is, even in Excel. Okay, so now just to finish up, I'll show the QuickSense integration. So again, this is only going to be showing a forecasting example, and in fact, this is not on the manufacturing dataset. Just because we haven't ported that manufacturing dataset over to the QuickSense installation we have yet. But just as an example, this is a different dataset based on a bike sharing scheme from Washington, D.C. So the aim here is to forecast out the number of users using the bike sharing scheme over time. And we have some other variables like whether it's a public holiday or not on that day, the temperature, humidity, wind speed, and so on, all the things that might affect whether someone is likely to use the bike sharing service a lot or not. So right now we have a 24-hour forecast. I can change the forecast length to 168 hours, which is the number of hours in a week. So that will be forecasting out bike sharing usage over the week. And when it's finished, and note again that TIM is building an entirely fresh model when I change that parameter. So we'll see the results will come back. And now we can compare the forecast to the actual. So the red line is the forecast and the blue is the actual. So you can see kind of how accurate the forecasts are. You can see these interesting patterns where on certain days you have this you have two peaks. One is around 8 a.m., the other one is around 5 p.m. So these are people commuting on weekdays, maybe also going out for lunch in the middle of the day. Whereas these are weekends, where it's a different pattern. It's a bit broader, centered around kind of 2 p.m., 3 p.m. or so. So that represents weekends. People are getting up later, going for brunch or whatever, going for a bike ride in the mid-afternoon. In the extension, in the ClickSense extension, we can also see all of the transformed features in detail, like we're seeing in the Tim Studio app. We can also see a simplified view, which just shows us the relative contribution of the raw features. In this case, there are just 6 of them, including the count of registered users, the temperature, humidity, and so on. So we can see the historical count of registered users as the most predictive variable in this case, which stands to reason. What happened last week or yesterday with the number of registered users is likely to have a strong effect on what happens today, but also the temperature is a strong predictor, and these other variables as well. So I think that's everything I wanted to show from the demo. So thank you for listening.